we have this integral. It's a nice one. It's basically begging you to use something. Do you see what this thing is? I mean, probably if you're here, then you do not see it. Or maybe you saw it, but you made a mistake in the computation. It's begging you to use partial fractions. How do I know this? I don't know, I just know it. Maybe you've not seen this before, so you wouldn't know or read that it is begging you to use partial fractions. So I don't blame you if you don't see it. You don't listen to the expression, saying, please use partial fractions. Please help me. I mean, I don't think the expression really say that, but it's almost like this. So what is partial fraction in the first place? It is just some theory that says that if you have a fraction and you have three things being multiplied by each other in the denominator, and these things are not the same, so they all have a power of 1. In our very specific case, they have a power of 1. So 1, 1, 1. So for example, we don't have something like this, then we can split them into 3 fractions. And on top you always have 3 constants. And the job of partial fractions is to compute the constants. And they are computed using something called the cover-up method. So A is the coefficient of x plus 1. So I do 2 things, maybe 3 things. I remove x plus 1 from the expression. I look for the value which I can plug into x plus 1 to get 0, so the problematic value, which is minus 1, because minus 1 plus 1 is 0. And I use this value, this red value, minus 1, and I plug it in for every single x in the expression. Now, I'm too lazy. I don't think in the exam you have a calculator, but because I'm a lazy person, I will use my calculator here. Actually, it's more difficult to use my calculator. I'll just compute it. This will be minus 2. This will be 1. No, this is 2. This is 1. So we're dividing by 2. 2 times 1. And on top you have 11. Here you have minus 12. So that's already minus 1. And here you have 3 plus minus 1, which is 2. This will be 1. Amazing. Okay. Can you pause the video and do B and C? That would be amazing. You could. So you get the expression. You cover up the coefficient of B, so you bring it outside the expression. You find the problematic value. It's minus 2. You plug it in here. And then you compute. So you would get minus 2 plus 3 is 1, minus 2 plus 1 is minus 1. So you would get minus 1 in the denominator. Minus 2 squared is 4, 3 times 4 is 12. Minus 2 times 12 is minus 24. Plus 11 is plus 11. 12 plus 11 is 23. So 23 minus 24 is minus 1. Minus 1 divided by minus 1 is 1. And maybe just to force you to actually do C, I will not compute it. I'll just say it out. So funny enough, it will also be equal to 1. You should check this. use the same way, please. And then when you do this, then it's very nice, because our integral, if I call it I, then my I is equal to this integral, yes, but instead of the clunky expression, I can just plug in these three nice expressions, which I can actually write as three separate integrals. Yeah, this should be possible. But you know what, it's fine. I don't need to write those three integrals, it's fine. It's fine, man. Just don't worry about it. But this has a very simple integral. Antiderivative. So we know that the derivative of ln of x is 1 over x. And here it's a bit similar. I just need to make a small modification, which is instead of x, you can just put in x plus 3. That is the modification you need to make. So that's something. So this will give you ln of the absolute value of x plus 1 plus ln the absolute value of x plus 2 plus ln the absolute value of x plus 3. Now, if you're wondering why we have the absolute value and not just x plus 1 or x plus 2 or x plus 3, because the original expression is defined for any x. I can plug in positive values in this expression. I can also plug in negative values in this expression. But if I plug in, let's say if I try to find ln of minus 1, then this is not really defined for real numbers. And so, to make sure that everything is consistent and to extend the domain of ln to take negative values, I need to consider the absolute value. Because otherwise it's not really defined. Now, please do not forget to consider, why am I torturing myself? I'm always torturing myself with space. Anyway. So do not forget to include the boundaries of integration. I hope you see why we use the absolute value. Before I apply the boundaries of integration, I would like to make a simplification. So if I am adding ln functions, there is a nice property of ln functions, which says that you can actually just multiply the terms. So ln of x plus 1, ln of x plus 2, ln of x plus 3 would be x plus 1 times x plus 2 in the absolute value times x plus 3 all in the absolute value. Maybe I'll just write one big absolute value for all three. So this doesn't look too bad. Maybe it looks a bit bad because it's a bit small. I don't like how small it is. But anyway, but this is nice because then I can plug in values, in one compact term. I'll just get ln of something minus ln of something. That's what I care about. So I would get ln of the absolute value of 1 plus 1 times 2 plus 1 times 3 plus 1. That will be 2 times 3 times 4 minus ln of 1 times 2 times 3. If I plug in 0, 0, 1, 0, 0, 0, I get 1, 2, 3. Now, to simplify this even further, just by the same property of ln, if I have a minus, then I can just write it as a division of the two terms. I can write it as 2 times 3 times 4 divided by... Well, I can get rid of the absolute value now because these are clearly positive numbers. So that's not too bad. So just like the previous property, there's a minus between ln's, I can divide the terms. So in the denominator, I would have a term which has the negative coefficient. And then we would get this very nice setup. Of course, the 1 just cancels out. It's a 1, I don't need to write it. Then in this case, the answer should be ln of 4. And I take a look at the choices. There's no ln of 4, but there is twice of ln of 2. And the reason why this is equal is because twice of ln of 2, you have the nice property of the ln that you can bring the power inside, the coefficient inside as a power. So you get ln of 2 squared. And guess what? ln of 2 squared is equal to ln of 4. So to solve this exercise, you need to, number one, know partial fractions and apply them, of course. You need to notice that you have a complicated expression in the bottom and you need to simplify it. So you try out partial fractions, you see that it works. It would work ideally when you have these terms to be all linear, so all to the power of 1, and all different. Then you have the classical ln absolute value integral. You can of course verify that if you take the derivative of this, you would get this, or you would get that, and so on and so forth. And then you just use some properties of logarithms to bring the answer to its final form, or at least the form which you would find in the choices. But any of these is actually an acceptable solution. I think if you write 2 times 3 times 4 minus 1 times 2 times 3, I think this is already very good. If there are no choices, I think this answer would be accepted. Maybe you would take away 1 point, but I don't think it would be this rough with the grading process.